We're going to do the lab here, part number one. We got water on the left and we got isopropyl alcohol on the right. We're going to swipe the countertops and see which one evaporates first and which one evaporates second. So we do a swipe at the same time. We can do our observations. Our observations are telling us that we have isopropyl alcohol on the right has evaporated. It evaporated first, and water has not evaporated yet. So we're going to draw these molecules to get a better understanding of what's going on here. So we're going to draw water, Lewis structure. So we have H bonded to O and then bonded to an H, making my skeleton. Got to give them what they want. This is what they want. Got to add up the valence electrons. Hydrogen has 1. There's 2. For a total of 2. Oxygen has 6, and there's 1. So 6 plus 2. This drawing needs a total of 8 valence electrons. Count them up: 2, 4, 6, 8. That's correct. And so we have non-bonding domains, 1, 2, and then 2 bonding domains. And so this is a bent molecule. When you have non-bonding electrons on the central atom, it is automatically polar, but you got to be advised or be careful of, well, is that polar molecule, does it have hydrogen bonding going on? And it is correct. We have hydrogen bonding going on in water because we have an H directly bonded to an O. And so there's an H bond there. That right there. Sorry about that. And so that is the most predominant. It is a polar molecule, but it has hydrogen bonding going on. And not only does it have a hydrogen bond over here, it has a second hydrogen bond. So when you have a molecule, you can actually add up multiple hydrogen bonds. So we have an H bond for water. So this is the structural formula for isopropyl alcohol. So we have a CH3 group. Anytime you have a CH3, so the C has 3 H's attached to it, which means this C here is actually attached to another C here. Okay, so it gets kind of weird. Well, you can't attach an H to anything else if it's attached to something. And so attached to this C, we have an H. And so we can put an H here. You can put it on the bottom if you want. And then this C here is actually attached to this O. And this O here, this H is attached to that O. Because you can't connect this H to the O and then have this C connected to the H, because hydrogen can only accept one single covalent bond, which then leaves us with this methyl group here. I think of methyl, or it could be ethyl, I can't remember, 1 or 2. That'd be that organic stuff. So anyway, so that's the structural formula. I got to give the oxygen here what it wants. And so we're going to look at it, and this is a more advanced molecule, but we're looking, this is a bigger molecule. This one evaporated first. This one evaporated second. What type of intermolecular force does isopropyl alcohol have? We have some CH3s here. CH3, well, anytime you have nothing but C's and H's, that is a non-polar portion of the molecule. But we're looking for what is the biggest intermolecular force out of the total. If you look at your formula, we have an OH, an O attached to an H, or an H attached to an O. So this one here has a hydrogen bond in it, okay? And so that is also strong. But when you have ties in your intermolecular forces, this is an H bond, but this one evaporated first. What can we say about why did it evaporate first when they both have the same strength? Well, sometimes we look at the tiebreaker is the number of electrons, but not in this case. It is if they're both the same force or intermolecular force, and what is the tiebreaker, and why do we have this one evaporate before this one over here? We have fewer H bonds. So if you have multiple H bonds, you're going to have greater attraction for that molecule, which means water has 2 H bonds and it's going to evaporate slower because it has a greater attraction to other water molecules and stays a liquid longer. So you got to look at the molecule and count the number of H bonds. More H bonds, the stronger the intermolecular forces, the longer it takes to evaporate.